Thank you, Nancy. My only regret is that I can't stay here long enough to audit one of your courses. But it's been a wonderful experience coming here for the first time, seeing old friends, meeting new people in the mathematics and computer science departments. And what I'd like to do is tell you about a sort of fairly novel viewpoint on the role of the theory of computation in relation to neighboring scientific fields of science, engineering, even social science, and also commerce. So we use the metaphor of the computational lens. We think of the theory of computation as shedding light on problems that arise not through the inner logic of computation, but through looking at computational phenomena that occur in other fields. So the basic premise behind this approach to broadening the theory of computation is that many phenomena in a wide variety of sciences involve information processing at a fundamental level and can be studied through computational models. So if we look at multi-agent markets on the web, or the operation of a living cell, you can think of those as computational phenomena that can be modeled and add to the breadth of theoretical computer science. So let me give you a little bit of history. This talk will be interwoven with comments on the historical development of this point of view and its influence. I came to Berkeley in 1969. My closest colleagues in that early period, Manuel Blum and Eugene Waller, came around the same time. And through the 70s and 80s, we had a very successful program studying basically complexity, cryptography, algorithms. Some of the topics were NP completeness, online parallel and randomized algorithms, cryptographic protocols, program result checking, where you study whether you can check the result of the computation for validity by some more efficient means than actually repeating the computation. During that period of 2 decades, we had a wonderful collection of graduate students and postdocs, some of whom are listed here, and many of them went on to professorships at leading universities and positions at leading research labs. One of the highlights of the latter part of that period was the work on probabilistic checking of proofs. This was an amazing outgrowth of the earlier work by Blum and his students on program result checking. So we know that in theory of NP completeness, we have this notion of verifying the correctness of a solution, verifying that a graph has been colored with a given number of colors, or that you have found a satisfying assignment to to a Boolean logic problem. But what this theorem showed is that it's quite paradoxical, because usually you think of a proof as being only as good as its cheapest link, as its weakest link. And so you have to check every step very precisely and completely. But Aurora and Safra show that you can actually develop at the cost of a polynomial size expansion in the proof, in the length of the proof, you can develop a new format for proofs where verifying the proof can be done by simply checking 3 or 4 random locations within the proof and seeing whether consistency holds. So a simple example would be verifying that an algorithm computes a linear function. And one way to do that is to pick 2 arguments, A and B, and just show that, check whether f of A plus f of B is equal to f of A plus B. And it turns out that if you do that in a few places, you have a high likelihood of discovering any error in the proof. Subsequent to that rather paradoxical discovery, some of our students and others at Bell Labs showed that a consequence of the existence of these probabilistically checkable proofs was that you can prove that certain NP-hard problems are not only hard to solve exactly, subject to the assumption that these are equal to NP, but they're even hard to solve approximately. So even with a large approximation error, so that, for example, it's hard to check whether a graph, to distinguish between graphs where the largest independent set is tiny and graphs where the largest independent set is huge. Crucial results on hardness of approximation stem from this notion of probabilistically checkable proof. So these were the kinds of things that we were doing in the 70s and 80s, but in the early 90s, partly because of the new cast of characters on our faculty, we began to reach out in different directions than the traditional complexity in cryptography. So there were several of us who sort of independently moved in directions motivated more by the sciences. In my case, it was genomics, and my motivation was to try to contribute to the Human Genome Project. And so I began working on combinatorial problems in genomics, string matching, genome assembly, some of the things that I talked about in yesterday's lecture. And I actually left Berkeley for a few years for various personal reasons, but also because genomics was very active at the University of Washington. And so I spent 4 years at the University of Washington learning about the biotechnology and the Human Genome Project. And it was an interesting, humbling experience because I would be sitting at the feet of the postdocs in the lab trying to understand what they were doing and admiring how much they knew, and then they would turn around and ask me to write a letter of reference for their job search. Eventually, Berkeley sort of started getting more motivated to develop computational biology, and I was invited back to Berkeley to help with that development, and many others helped, and we now have a computational biology center with about 30 faculty studying genomes and phylogenetic trees and population biology and synthetic biology, protein structure, a whole bunch of different problems in biology that are computational in nature. So that was an example of one direction of outreach, trying to apply and extend the theory of computation to another field. Another colleague, Umesh Vazirani, went in the direction of quantum computing and continues to go in that direction. So he discovered a fundamental paper by Richard Feynman called Simulating Physics with Computers, and in particular the simulation of quantum systems. He began thinking that a computer that's based on principles of quantum physics might be more powerful than a classical computer. And in a fundamental 1997 paper with the student Bernstein, they developed quantum complexity theory. They laid out a formal model of quantum computation analogous to the Turing machine and began to study complexity classes. And the fundamental difference between quantum computing and classical computing is that whereas the basic unit of information in classical computing is the bit, which takes up values 0 or 1, consistent with quantum theory, the basic unit of information is what's called a qubit, which actually is represented by a probability distribution involving two complex numbers, but with the property that even though there's a huge amount of information in the qubit, when you observe the qubit, it lapses probabilistically either into the fixed value 0 or the fixed value 1. So the fundamental issue with quantum computing is how can you harness the richness of these basic informational units, which are so much more rich than an ordinary bit, subject to the observability restriction that when you observe, you probabilistically get a fixed bit, 0 or 1. And Umesh has continued, many others have continued to pursue this direction. And one of the purposes of the theory of quantum computing is to provide tests to see whether the underlying principles of quantum physics actually hold. So it may be that one outcome of the study of quantum computing would be to discover a violation or a necessary extension of quantum physics. The third direction, which was adopted by another colleague, Alistair Sinclair, had to do with statistical physics. Statistical physics is basically the study of systems of interacting data entities that represent, for example, atomic spins or magnetization and so forth, where the models are taken to be probabilistic. So there becomes, and you study certain phenomena like the freezing of water into ice, which correspond to what's called phase transition at a certain temperature. And because you're basically studying large, discrete stochastic models, there is a close mathematical relationship between studying these statistical physical systems and studying randomized algorithms. So Sinclair wrote some fundamental papers. One of them had to do with the approximation of the permanent. This is a special case of this problem is the problem of counting the number of perfect matchings in a bipartite graph. This paper showed that if you construct an appropriate Markov chain whose states are the possible matchings, then by sampling from that chain, you can actually get a very close approximation with high reliability for a problem that we don't know how to do deterministically. And so there was this interplay between computer scientists using ideas from statistical physics, such as the study of rapid mixing of Markov chains, and trying to apply these ideas to computation. And the physicists had wonderful insights which they didn't know how to turn into rigorous theorems, but which were generally correct. And the computer scientists and mathematicians had technology for writing rigorous proofs, but they had to understand the ideas of what the physicists were expressed in an unfamiliar language. And it was only around the year 2005, through a program at the Mathematical Sciences Research Institute in Berkeley, that the physicists, computer scientists, and statisticians came together and began understanding each other's language. And now the field has become very cooperative between those groups. And so here are a couple of examples of the interplay between statistical physics and the theory of algorithms, especially randomized algorithms. Randomized polynomial time algorithms for computing the number of perfect matchings in a bipartite graph are based on a certain Markov chain Monte Carlo method of sampling from the states of the stochastic system, a method that was invented by physicists for sampling the states of a system of interacting particles. The best known method for solving random satisfiability problems combines ideas from statistical physics with the belief propagation technique from computational learning theory. So we see a very intimate connection between these fields. So for example, phase transitions, where a statistical physical system makes a transition from, for example, freezing to melting or something like that, obey obey the same kinds of mathematics that are involved in showing that there's a threshold in a combinatorial problem, such as satisfiability, where the problem goes from satisfiable to unsatisfiable and we change the number of clauses, analogous to changing the temperature of the physical system. Another area is the confluence of economics and game theory, which became of particular interest to computer scientists with the advent of the internet and the web, where you have markets and other economic mechanisms that involve the behavior of very large numbers of agents, sometimes trying to cooperate, sometimes trying to compete, as in the case of auctions. The internet became the source of the starting point for new models of computation, totally different from the Turing machines that we're used to, but which are limited to one user solving one problem on one processor. And looking instead at this environment that the web creates, where you have all of these users interacting. Christos described the situation in this way. He said, we had to approach the internet with the same puzzlement to which previous generations had approached the brain, the cell, and the market. And some of the fundamental papers were one by Licio, my colleague, and another by Nissan and Ronan, who brought an algorithmic point of view into mechanism design. Mechanism design in economics means the design of mechanisms for interaction to achieve some end. You might want to design an auction to maximize revenue, or you might want to design an auction to induce the players, to the participants, to tell the truth about their preferences. Rafgan and Kardosh studied another problem which has to do with the collective behavior of many independent, selfish agents. And the setting that they considered was a simple situation where people are driving from point A to point B through a network of roads with different capacities. It turns out that if everybody tries to pick the least congested path, then you'll get a higher level of overall cost and overall congestion than you would if an invisible hand could direct the cars to go in the go pattern. So this is called the loss occurred by selfish driving. So basically, this new model of computation is extremely rich because the internet and the web are simultaneously computational, social, and economic, and they involve both computation and communication into a host of novel algorithmic problems that have arisen in connection with the phenomena on the web. Problems of ranking web pages, of estimating the reputations of individuals based on the opinions of others, recommendation systems, design of auctions and other economic mechanisms, optimal placement of online advertising. So it's a whole new world of applications for algorithmic ideas stimulated by technological development, namely the web. Other work is related to social networks. For example, John Kleinberg studied the 6 degrees of separation phenomenon that you may have heard of, where, as the story goes, if you want to send a letter to a person in a remote location whom you don't know, and you can only send it to somebody that you are personally acquainted with, then you could try to forward the letter to somebody who you think might be closer to your target than you are, and have that person instead in turn forward the letter. And there's some empirical work by sociologists indicating that if the letter gets through at all, it will probably get through in 6 hops. And that's called the small world phenomenon, and Kleinberg gave a theoretical explanation not only of the small world phenomenon, but of how you would, the strategy that you would use to direct your letter. less valiant wrote an early book trying to understand some of the limitations of the brain by thinking of the brain as a kind of graph or circuit. So these were some of the early examples of turning the algorithmic lens towards other areas of science. So the group at Berkeley discovered that we had in common this viewpoint on theory of computation as reaching out to the sciences. And so we went for an NSF grant together, and we were funded to continue working in these different areas. And we held a conference at Berkeley to celebrate the inauguration of the grant, and we invited people in all of these areas and more who were somehow representing areas where theory of computation could extend. And we found, very interestingly, that these people who had very different interests ranging from astronomy to genetics still appreciated this general viewpoint and could communicate very well among themselves. And in May 2011, we ran another conference, again on the computational lens, applied to a whole batch of additional areas, the ones I mentioned already: social networks, genetics, cognitive science, machine learning. Machine learning has become increasingly important as a very broadly applicable tool in many scientific fields, and so machine learning and big data are intimately involved with this point of view that we're taking. Other places got the same idea, more or less independently. Caltech decided that it was time. Caltech has been a giant in the physical sciences throughout its entire history. They decided that it was time to bring information science and technology up to a high level in Caltech as well. And in inaugurating that activity at Caltech, the famous biologist David Baltimore spoke about the changing role of information science. He said, "Some say biology is the science of the 21st century, but information science will provide the unity to all of the sciences." That's kind of an interesting claim, that information science is going to be the science of the 21st century. Information science, the understanding of what constitutes information, how it is transmitted, encoded, and retrieved, is in the throes of a revolution whose societal repercussions will be enormous. So he foresaw how the information science viewpoint could be pervasive in different scientific fields, and they chose 4 areas to investigate from this point of view: biological circuit design, social and information sciences, physics of information, which is related to quantum physics, and mathematics of information. And they had a thriving postdoctoral program, and one of the rules that they enforced was that every postdoctoral researcher had to have mentors from 2 of the 4 areas, so they were very interested in the mixing and interrelationship of these different areas. Now, around the middle of the first decade of our century, there was a lot of worry in the field of theoretical computer science that somehow we were having increasing difficulty funding our research, and we felt that we had to do something making the National Science Foundation aware of the importance, as we perceived, of what we were doing. And some people from Princeton and the Institute of Advanced Study wrote a white paper pointing out this difficulty in getting out funding for theory research. And the Professional Guild for Theoretical Computer Science, called SIGAC, appointed a committee with the membership shown here to try to do something about this situation, and I became the chair of the committee. And we submitted a white paper proposing a new program of research on the theme of the computational lens. So we laid out the idea of influencing the sciences and generating new models arising from the sciences. And this was warmly received by the people at NSF because they were grasping for ideas that they could present to Congress to get more money. And so this led eventually to something called the Cyber-Enabled Discovery Initiative, which actually brought them quite a bit of money. But in the course of developing it, the pure message that we had started with got watered down. And so by the time they finished engaging in political dialogues with all the other branches of NSF and making something that everybody could agree to, our basic concept had been distorted almost beyond recognition. And the program instead became a catch-all for all activities involving the interaction of computer science with other sciences, even those which were not necessarily innovative from computer science alone. So it was kind of a mixed thing. I guess we felt that we had contributed by catalyzing a process that eventually led to a big jump in NSF's funding for computer science, but at the same time, we felt that our original message had been somewhat lost. In any case, in the course of working with NSF, we held additional workshops which were called Workshops on the Computational Worldview of Sciences, so the same basic message. And the range of activities where we could see computational models contributing was broadened. So neuroscience, theory of evolution, synthetic biology, DNA computing, nanotechnology, self-assembly, brain modeling, etc. Even the flocking of birds and cosmology were introduced as examples where new theoretical models of computation could arise. And the workshop report, there were actually two workshops, one at Caltech and one at Princeton, laid out some of the open problems. Is a crowd of quantum particles different from a few particles? So this arises because of the interest in quantum computation and the phenomenon of entanglement of qubits, the phenomenon where you get a correlation between the values of two different qubits that are physically separated. And the question is, people have really studied fairly simple systems with not too much entanglement between the different qubits. But for quantum computing, you would have more complicated setups where you would have entanglement or correlation of many different qubits. And so the study of quantum computation could potentially lead to the discovery of a violation of quantum mechanics. Another area was non-equilibrium dynamics. Instead of just studying the stationary distribution for a Markov chain, you would want to, for example, you would want to study the rate at which converge to the stationary distribution. Algorithmic game theory has become the recognized setting for the various economic mechanisms involved in the World Wide Web. New models of the brain, modeling regulatory processes in living cells, social networks. These were some of the examples that were pointed to as open problems in the workshop report. Around the year 2009, there was a further development that involved the Simons Foundation. Jim Simons is a famous mathematician for his early work with Chern on something called the Chern-Simons theorem. So he was a very noted mathematician, but quite early in his career, he took a different direction and became a hedge fund manager. And he is the most successful hedge fund manager of all time, and earns billions of dollars every year. And through methods that are not publicly known. His company has assembled a first-class collection of mathematicians and statisticians. And Jim Simons and his wife Marilyn founded a foundation to support research. Their first efforts were in the direction of supporting autism research. They have an autistic child, and so that was a particular interest to them. But he also did a lot of support of mathematics, and at a certain point, he decided to systematize his philanthropic activities and organize them through a foundation known as the Simons Foundation. So I attended a committee meeting at the foundation around 2009, and his wife Marilyn, who's actually the president of the foundation, was telling us about how they got into this philanthropy. She said, you know, Jim had been doing various philanthropic things, and he decided to systematize it. So he put aside a couple of $1 million, and he invested it on behalf of the foundation. Pretty soon they had 60 million, and he decided that they really had to do some things for mathematics and related fields. So there was a meeting at Simons Foundation in the year 2009 where they were looking for new things to do. And mathematics already had a number of institutes, mainly supported by the National Science Foundation. There was no corresponding entity for theoretical computer science. So Avi Vickerson, Margaret Wright, and I proposed the creation of an Institute of Theoretical Computer Science. And after some discussion, they decided to go for it. And one of the founding documents said the new institute will be focused on research in theoretical computer science broadly defined, including its theoretical core agenda as well as its joint endeavors with mathematics and the sciences. So the goals of the Simons Institute for the Theory of Computing were following: to create a leading international center for research in the field of computation, to strengthen the field's core and foundations, and most significant, extends beyond current reach of the field. And there was a competition over a couple of years, and eventually Berkeley was selected as the location. We officially were inaugurated as an institute in July of 2012. And the way the institute is going to be operating will be more or less in a revolving door fashion, with a different crew of visitors every semester. And these will consist of postdocs, students, and senior scientists. And it will be focused on, in each semester, typically on 2 research programs, which will be conducted in the course of the semester and then continued afterwards, where the postdocs will return to their home institutions or go on to other jobs, but they'll stay in touch with the program and with their mentors. We're beginning a full-scale operation of the Institute in August of this year. We haven't been able to do it sooner because we've been busy renovating the building where the Institute will be located. So this spring we haven't had full-scale operation, but we will be running a symposium on visions of the theory of computing. I'll say more about that in a few minutes. And there's one other exploratory meeting. But now we typically plan our programs about 2 years ahead. So the programs for the 2013-14 academic year and for the fall of 2014 have been established. And you can see that it's a mix of sort of core theoretical computer science with outreach to other fields. So we have, for example, real analysis in computer science. This is really an inner activity of theoretical computer science, applying classical mathematical analysis to discrete structures like Boolean functions with applications to learning theory and communication complexity and economic social choice. But mixed in, we also have a number of more areas with more flavor of outreach, such as evolutionary biology or theoretical foundations of big data, where the participants will study some of the fundamental statistical and algorithmic problems involving the massive data sets that are now occurring in every field. In particular, I want to invite you to a symposium that we're running from May 29th to May 31st. By the way, Nancy Amato is responsible for the layout of this slide. I am not very good at PowerPoint and could not have done this myself. And you can see the kind of mix of outstanding speakers that we're going to have, including computer scientists whose names are likely to be well known to you, but also leading people in bioinformatics and neuroscience and statistical physics and quantum physics and economics, chemistry, and so forth. So we'll be gathering these people together as well as representatives from cutting-edge industrial companies like Google. So I hope that some of you will mark your calendars for May 29th through 31st. Registration is free. You just have to get yourself to Berkeley, and the rest will be taken care of. Let's see how I'm doing on time. I have a little bit of time left, so let me give a few vignettes of how models from the theory of computation are motivated by and contribute to various branches of science. So Joshua Bloom, who's one of the speakers at our May symposium, is working on technical and observational challenges for future time domain surveys. So this has to do with optimizing the use of the resources of telescopes that are scanning the night sky to find new phenomena. And so these telescopes are generating images of the sky, which then have to be analyzed in real time to determine whether they're dull and uninteresting, or whether they're capturing some novel cosmological event. And so there's the problem of real-time control of these robotic telescopes to determine at every moment where they should be looking and to control them in parallel with analyzing all of these many images that are being generated. So the robotic telescopes are believed to be effective alternatives to the traditional role of the astronomer, using unaided human judgment, more or less, in planning and conducting these time domain observations. So there's a lot of decision theory and computer science that's involved in organizing this decision process of deciding where and when to look in the night sky. And the prediction is that automated algorithms will play a much more central role as this field develops. So that's one example of the kinds of new applications that we're considering. Another field that's been more or less revolutionized by the advent of the internet and is now guided by algorithmic considerations is advertising. So here's one example of a problem that has been formalized in this area. The problem is basically to decide which web pages should be listed in the response to a search, in response to a keyword search. So how does a search engine company decide what ads to display with each arriving query, usually a keyword search, to maximize its revenue? So this was formulated as a as an optimization problem by the 4 authors shown above. And it turns out to be a generalization of a simple problem that I worked on earlier with the 2 Vazirani brothers, Umesh and Vijay. And the problem is the following. I'll put it in terms of matching boys with girls. Suppose you have n boys and n girls, and this is the classical bipartite matching problem that you would like to pair them up in some fashion. So for example, you might want to have information in the offline version of the problem. You would have a matrix that tells you, a matrix of zeros and ones, which will tell you for every boy-girl pair whether the boy and the girl are compatible, and then you could compute on this matrix using network flow techniques to find the biggest possible matching of boys one-to-one with compatible girls. But the problem that we considered was an online version of the problem where the boys come along one at a time, let's say in random order. And for each boy, you're told which girls the boy can be matched with. And you have to decide in online whether to match the boy with one of those girls, and if so, which one. So the point is that you don't have full information. You're only learning about, for each boy in turn, you're learning what matches are possible for that boy. But there are easy examples showing that you can't expect to get the maximum matching. But how well can you do? It turns out that a deterministic algorithm, an algorithm that doesn't make random choices, cannot guarantee a matching bigger than half the size of a maximum matching. But we were able to show in this paper that a randomized online algorithm can actually achieve a fraction 1 minus 1 over e, which is about 0.63 of the size of a maximum matching. And this number, 1 minus 1 over e, keeps showing up in subsequent papers that involve different kinds of matching. And in the paper by the 4 authors here, the matching is between advertisers and slots associated with different queries. So it's essentially a matching between queries and advertisers. And they were able, with a proof much more complicated than ours, to show that for that problem as well, they could achieve an approximation ratio of 1 minus 1 over e, where e is the base of natural logarithms. Game theory is kind of the branch of mathematical economics which encompasses all of the kinds of adversarial situations that arise in allocation of resources on the web, markets, auctions, and so forth. So a game is really a situation of conflict among several players, where each player has a set of strategies, in our case a finite set of strategies, and the joint payoffs to all of the players are a function of the joint choices of strategies that they adopt. The players can also play, so an example would be, a simple example would be matching pennies. You know, we each have a penny, we pick heads or tails. If the pennies match, I win. If the pennies don't match, then I lose. How shall I play? Well, if I play a deterministic strategy, like always playing heads, then my opponent can slaughter me, obviously. But if I randomize, I can, just picking randomly, I can establish 50-50. So randomized or mixed strategies can be better than deterministic ones. And a famous result by John Nash is that every game has a Nash equilibrium, which is a joint choice of mixed strategies, so that if the other players play their mixed strategies, you cannot benefit by deviating from yours. So it's a Nash equilibrium where you allow mixed strategies, is a set of choices where nobody is motivated to deviate. And the Nash equilibrium is taken to be as a reasonable abstraction of the notion of rational play, but there are some difficulties with the Nash equilibrium because a game can have many, many different Nash equilibria, and the theory doesn't really tell you, the basic theory doesn't tell you which one to choose. Game theorists never seem to worry very much about how you could compute a Nash equilibrium. They were very pleased to prove by a non-constructive method that a Nash equilibrium always exists, but it was left to the computer scientists, in this case Daskalakis, Goldberg, and Papadimitriou, to study the computational complexity of computing a Nash equilibrium. And they actually showed that it's an intractable problem. For those of you who are into computational complexity theory, it's a PPAD complete problem. So this raises yet another objection to the concept of Nash equilibrium. The objection that's usually lodged is there are too many Nash equilibria, and so you don't have a criterion for choosing among them. But now we have another issue, the computational complexity issue, which can be expressed in this following way by Kamal Jain. If my laptop cannot compute a Nash equilibrium, how can the market do so? If the computation is intractable, how can we expect the market to arrive at a Nash equilibrium? So this is an example, among many, of the interplay between economics and computer science in the realm of mechanism design and game theory. Yesterday I talked about computational processes in biology, focusing on regulatory networks in cells, looking at molecular biology, but biology at all levels is full of computational processes that beg to be analyzed from the viewpoint of computer science. Learning in neural networks, the algorithm, so to speak, that the immune system follows in responding to an invading microbe, embryonic development, cancer as an algorithm gone wrong, flocking of birds, synthetic biology, and evolution itself are examples at many different levels of computation processes in biology that naturally can be considered as computational. And yesterday I talked about the particular example of molecular biology. I won't repeat that discussion. So that brings me to the end, and I'll be happy to take questions. Surely there's at least one question. How can this be? Yes, good.
Is the universe computational?
Is the universe? Why do you? I don't want questions like that. Is the universe computational? I would like to think that it's governed by the principles of physics. That's my belief, I guess, but I'm not an expert. Yes?
Yesterday you said that many of these problems are NP-complete.
Yes.
And you have to attack them heuristically.
Yes.
And you suggested some idea of how good the heuristics might be. So would you like to comment more on that? What sort of statistics, if you're taking a heuristic approach to an NP-complete problem, what can you expect for how well it will work?
Okay, so the question is, if you take a heuristic approach to an NP-complete problem, what can you expect as to how well it will work? So this is a somewhat mysterious area where the existing theories, in my opinion, are not adequate. There are basically
two branches of theory that relate to this question. One of them has to do with what are called approximation algorithms. So many of these problems are not just yes-no decision problems, but they involve optimizing something, like coloring a graph with a minimum number of colors, or finding the best solution to an integer programming problem, and so forth. So you have a notion of an objective function, and if you can't compute it optimally, you could still ask, how close can you come? What ratio can you achieve between the actual maximum value and the value that the heuristic can achieve? So there are a number of results along those lines. Some of them are positive, saying that various problems can be approximated within a certain factor. And some of them are negative, showing that if p is unequal to np, then you can't get a decent approximation at all. I alluded to that earlier. I don't find that line of research very satisfactory, because in evaluating approximation algorithms, it focuses on the worst case approximation ratio possible. One molecular biologist said to me, why do I want to listen to these guys who can solve the problem within a factor of 10 when I can solve it within 1% almost all the time? And so we would really like to have a theory of approximation algorithms which would tell us how well we can do on typical problems. But what do we mean by a typical problem? Well, you can define a probability distribution over problem instances. So if you have a problem where the input is a graph, you might assume, one of the classical models says that we'll assume that all graphs with a given number of vertices and edges are equally likely to occur. And then you can prove some very nice theorems that certain basic problems can be solved very well on almost all graphs. But why would anybody think that the examples that come up in practice are drawn from such a simple probability distribution? So that kind of so-called average case analysis doesn't seem to do the job either. And so we don't really have, and I think it's one of the great mysteries, we don't really have an adequate theory. My present belief is that the present direction that I'm pursuing is to take a page from computational learning theory and to ask the following question. Suppose that there is a source of typical instances available to you. You don't have a mathematical description of it, but you can draw randomly from that space of typical instances. So, for example, if you've been dispatching taxi cabs in New York City for many years, you have many examples of previous taxi cab dispatching problems, and you can think of those as a training set, and it would be reasonable to assume that future examples would be similar. So one approach would be to show, perhaps empirically, that a certain algorithm does well on the training set, and then you could have some confidence that it would also do well on future examples. And so that's a direction that I'm interested in. But I would say that overall, we really don't have the right theory for evaluating heuristics. They often behave incredibly well. For example, the classical prototype of NP-complete problems is the Boolean satisfiability problem, which is considered a hard problem by theoreticians, but people in integrated circuit design or or hardware verification think of satisfiability problems as easy, because the instances that tend to come up in the applications for some unknown reason are really quite easy. So we need a theory that would capture that kind of phenomenon, and we just don't have it right now. Way there, back there.
You talked about how computer science can help biology. Can you think of instances where biology or the natural sciences may inform how to do computation?
Right, so you're asking, are there situations where biology can inform computation. Well, I think there are a few examples. There's the study of DNA computing where people use DNA as a computing medium and solve a satisfiability problem by creating a whole bunch of DNA molecules that represent all possible solutions and then use molecular biology experiments to throw away the bad ones and see if anything is left at the end. There are other, I don't find that a particularly promising direction, but more recently there's been a lot of work on molecular self-assembly where you use DNA not for its basic ability to be used in replicating itself, but just as a template for causing different patterns, creating patterns by causing different structures labeled with DNA to stick together, so molecular self-assembly. There's also other motivation from biology. For example, genetic algorithms are motivated by evolutionary theory, and they've been successful in some areas. But I'm not sure that I can think of too many other areas. Yeah. Yes?
So I would like to bring a question on the educational perspective.
Mm-hmm.
So as you argued, computational permeates all the branches of sciences, and there's a similar sort of activity going on called cyber physical systems,
Yes.
which tries to, cross the boundary between the physical sciences and information sciences as well.
Yes.
So, I think then in an educational question is, especially I guess perhaps on the undergraduate level, is
Yes.
given the limited time and the existing sort of a departmental setup,
Yeah.
how should we teach? Or I guess more importantly, what are the things we should not teach?
Yeah. It's very difficult. It's very difficult to throw things away. There are certain areas that are that were once central and are less central nowadays.
Has Berkeley done any trials, experiments on this?
We're just groping it. The way in which we're groping with it at the moment, well, first of all, having this institute that's going to reach out to all these different areas. But we're also very interested in the issue of big data, which we see as coming up in virtually every field, not only science and engineering, but actually humanities, social sciences, commerce, business analytics, everywhere you look. So everybody is going to have, would benefit from some notion of how to deal with huge data sets. And that's too big a challenge for a single department to handle. So somehow it has to be a cooperative emphasis across departments. In fact, when I heard about the expansion plans here at Texas A&M, I wondered whether you're giving consideration to changing the structure, because as long as you do it within the established departments, you may not have the flexibility that would be needed. So I think everybody has to learn something about computer programming these days, even if they aren't going to be programmers. They have to understand what an algorithm is. And I think in almost every field, people are going to have to understand big data and to have a sense of logical argumentation and a notion and a little bit of comfort with probability. And exactly how you build that in, I'm not sure. But it's got to be done. Yeah.
Any other?
Hi.
One more question.
Yeah.
I actually have a request, another question. So I'm teaching actually a graduate level algorithm analysis class right now.
Yeah.
And many students from class actually here. So right now we're learning NP-completeness.
Okay.
So I was wondering if you can make some comments or tell us something about many years ago when you studied NP-completeness, what happened?
How
do you go about the problem? That's been a nice addition to the class.
Okay. Very briefly. I had a lot of experience with various combinatorial problems. I had worked on design of logic circuits in the old days when you didn't have integrated circuits and you just, every transistor cost $1 and you were trying to minimize the number of transistors, or relay switches and so forth. I had worked on the traveling salesman problem and various other covering and packing problems. And I had a vague notion that these problems were really hard, but I had no sense of how to formalize it. I remember seeing a paper by George Danzig where he showed that in a certain sense, integer programming was a very general format that other problems could be expressed in. So integer programming had a great generality. But then I happened across a paper by Stephen Cook, a now famous paper from 1971 by Stephen Cook, where he really defined NP. It had been defined more or less by an earlier scientist named Jack Edmonds, who worked on matching and other problems. And Cook had this definition of NP and a notion of reducibility and the concept that every problem in NP was reducible to satisfiability. But he was approaching it from the point of view of a logician. And he didn't choose to delve into the practical implications of this. Whether he was aware or not, I don't know. But he just satisfied himself to show this initial NP completeness result. So I ran into this paper, and it was apparent to me that there are many, many other common problems that also were likely to be universal. And once I had that idea, the construction of the necessary reductions wasn't that difficult. They're not really that hard to find. So I gradually built up more and more examples of common combinatorial problems from commerce and engineering and science and so on that also had this universality that the satisfiability problem had, that any problem in the class NP could be expressed. So the stimulus came from Cook, and the experience came from working with real problems and putting it together. I was motivated to start generating these additional examples, which by now there are thousands of them. You know.
Wow, that was a perfect request, Andrew. Thank you so much.
Yeah.
So let's go ahead and thank Sue.
Thank you. Thank you.